Okay, hello and welcome back. In this video, we're covering section 3.3. We're going to look at another attribute of lines called the slope of the line. So we've been graphing lines using points and intercepts, and we'll look at another attribute that's very helpful in building the graph of the line, and it also tells us a lot of useful information about the line. So first, let's go into what the slope of a line is. So let's see how they define it. So the text says the slope of a line measures its steepness. It's the ratio of vertical change in y to the horizontal change in x. And then we typically use the letter m to describe the slope. So let's think about what this means. So we've been plotting lines and we've noticed that they have a certain kind of angle. Could have a line that's like slanted upwards, could be slanted downwards. And when I say upwards and downwards, I'm reading from left to right. You could say that's increasing or decreasing. Could also have a flat line. We saw some horizontal lines last time, and also vertical lines. So we're saying that slope is a measure of the steepness of the line. And it could be positive or negative or zero, or as we'll see, it could be undefined. So if we have an upward line like this one, some kind of upward slanted line, we would say that it has positive slope. If a line is slanted downward, reading it from left to right, it will have a negative slope. And if it's a flat line like this, we'd say that it has a zero slope. The slope would be equal to zero. Which makes sense. It's almost, imagine somebody walking on this. They're just walking on a flat surface. There's no slope to the line. Whereas positive slope, you would be walking uphill. Or negative slope, sliding down. So what about a vertical line? Can't really walk up a vertical line. In one sense, it kind of has an infinite slope, but we describe it as being undefined. It cannot be defined. An undefined slope. So that's this measure of steepness. And then it mentions it as the ratio of the vertical change in y over the horizontal change in x. So we can describe the slope as a ratio, so a fraction, where it's our change in y referencing like a coordinate point, xy, over or divided by the change in x. You may have also heard this described as rise over run, and that means the same thing. Where if we're on an xy axis, let's imagine some particular line on our coordinate plane. So let's add some divisions here. And let's say it goes through these 2 points. Let's say it goes through the origin and the point 3, 4. So that would be up here. So plotting a line using 2 points like what we've done previously. But now we'll be able to quantify how steep this line is. What is its slope? Well, if I view it as the change in y over the change in x, or the rise over run, I can just imagine from one point to another. So say like from our starting point, maybe let's label these 0, 0, and 3, 4. What would be the change in y from one point to another? can almost imagine a vertical line going up. Oops. So it's 1, 2, 3, 4 units up. That would be the change in y, or the rise. And then 3 units over, kind of builds a little triangle. You can see this as a distance of 4 and then a distance of 3. So if I was describing the slope of this line, I would say the slope is 4 over 3. Rise over run, or the change in the y coordinate divided by the change in the x coordinate. And we'll build a more specific formula where we can use 2 points. So let's do that next. So we'll be able to, without looking at the graph, find the slope of a line given 2 points on the line. So I'd like to show where the equation comes from. Let's build it kind of from scratch. Again, let's imagine we're on some line. And let's say we have 2 points here. I'll call this our first point, and I'll call this our second point. I'm going to call this point, instead of specific numbers, I'm going to just say generally, this is some x value. I'm going to call it x1 with some y value, y1, to say that they're coming from point 1, the x and y value. And so I can call this other point, this will be my second point, I'm going to call it x2, y2. So that'll be our second point. And let's still apply this change in y over change in x. So we can imagine building a triangle. We can say this would be some position on the x-axis. Maybe the x-axis is down here. We can call that x1. And then we can imagine this point being the second x value. Maybe this is like 2 and this is 4 or something, but let's keep it general. And we can do a similar kind of labeling for our y's. We can call this y1. Imagine that somewhere on the y-axis. And this would be y2. So how would we define this change in y over change in x? Well, this would be our change in y, this vertical distance. We'll draw it over the edge here. Well, if I wanted the distance between y2 and y1, I can just subtract them. I can take, since y2 is higher, I can take that point and subtract the lower point, and that would give me this distance. And then for the horizontal distance, I can do a similar subtraction. I can take whatever value this is and subtract this value, and that will give me the distance between them. So I can call this x2 minus x1. That's this horizontal distance. So let's put that in into a little equation. If we're saying that slope is rise over run, or the change in y over the change in x, we're saying the change in y is y2 minus y1. And the change in x, x2 minus x1. And let's use that letter m that was mentioned last time. We should use m to designate slope. So this actually is our slope equation. If we have 2 points, we can call the first point x1, y1, and the second point x2, y2. We can plug it into this formula and find out what the slope of the line that goes through those 2 points are, even without seeing the line like in person, without even seeing the graph. If we just know the 2 points, we can produce the slope. So that's what they're giving us here, this formula. y2 minus y1 over x2 minus x1. And we mentioned on that last page that this value will be positive if the line slants upwards from left to right. And this value will be negative if the line slants downward from left to right. So let's see a couple examples. In this case, we're given the graph as well as 2 points. So we can take two approaches. Let's just use the 2 points and find the slope. So for graph A, I know it's kind of small. Point A, I'm going to call that point 1, is 2, 3, and our second point is 4, 6. So we can label these. I can call this 2 my x1, the 3 is my y1, this 4 I can call my x2, and 6 is y2. So let's recall the slope formula. Say that m equals y2 minus y1 over x2 minus x1. And since everything is labeled, I just need to pick up the right piece and plug it into this formula. So our y2 was here, positive 6. So positive 6 minus y1, which is positive 3. So 6 minus 3 over x2 minus x1. So this will be 4 minus 2. 6 minus 3 over 4 minus 2. That will be 3 over 2. And that will be the slope of our line. And let's check this. Let's look at the rise over run on this graph. If we start at point A, we would go up 3 and then over 2 to get to our next point. And that's true between any two points on this line. Let's pick another one that's going through a nice corner of a square. If I start here and go up 3 and then over 2, I land on another point on the line. I can go up 3 again, 1, 2, 3, and over 2, land on another point. Up 3, over 2. So it will always describe, starting from one point, how to get to another point on the line. It's part of why it's very useful. So let's look at the other one. And notice this is positive and we have an upward slanted line. So let's look at part B. Our first point is negative 1, 2. And our second point is 4, negative 1. So again, I can label these. I can call this my x1, call this my y1. This will be my x2, y2. And we could have started with this point as our x1, y1 and call this x2, y2, as long as we're consistent. I wouldn't want to mix up the numbers and say x1, y2 for a single point. So let's plug into our slope equation. y2 minus y1 would be negative 1 minus 2 over x2 minus x1. That will be 4 minus negative 1. I'm going to put that in parentheses just to remind myself that the double negative is going to cancel. So 1 minus 2 is negative 3. And 4 minus negative 1, the double negative will turn that into a positive 1. It's really 4 plus 1. So our slope should be negative 3 over 5. Meaning from any point we would go down 3, since it's negative, and then over to the right 5. So let's try that out. From this point, let's go down 3, and then over 5. 1, 2, 3, 4. Or let me look at that again. Down 3, 1, 2, 3, then over 5. 1, 2, 3, 4, 5. Yeah, another point. We could go to the left 5 and then up 3. 1, 2, 3, 4, 5, and then up 1, 2, 3. We get another point. So that would be if we were viewing the slope as 3 over negative 5, like a rise of 3 and a run to the left of 5. So we can stick the negative on the top or bottom and it will still work out. So that's using this slope equation, y2 minus y1 over x2 minus x1 with 2 points. It's really helpful to label the points, your x1, y1, and x2, y2, and then you just need to plug into the formula. All right, let's look at it, some application of this. So this says the graph models the number of members of a certain health club from 2013 to 2017. So part A asks, how many members did the club have in 2013? Well, a point on this graph, the x value is the year, and then the y value is the number of members that it has. So just reading off that point, in 2013, there were 358 members. And then in 2017, there were 610 members. So the membership definitely grew. Almost doubled. So B asks us, what does the sine of the slope of the line segment mean in context of the problem? This line definitely has a positive slope. It's increasing from left to right. So the slope is positive. But what does this mean in context? It means that the membership is growing. The membership is increasing. I can say the number of members is increasing. C asks us to find the actual slope. Let's use our new formula to find the slope of this line going through the 2 points. So I'll call this 2013 my x1, 358 is the y1, 2017 will be my x2, and 610 will be my y2. So let's just follow the formula. I'll write it again here. y2 minus y1, change in y, over x2 minus x1, change in x. So y2 is 610 minus y1, which is 358. So it's the change in membership over the change in time. 2017 minus 2013. So 610 minus 358 should give you 252. And 27 minus 13 is 4. So what we're producing is a rate of change, kind of like miles per hour, but this is number of new members, and in this case, this is over 4 years. But if we divide this completely, we'll get number of new members per year. If you do 252 divided by 4, that should give you 63. That means every year the membership increased by 63 people. So let's write that in context and say number of members increased by 63 members per year. So this gives the slope this concept of a rate of change. And it's more obvious when we use it to model something specific, some growth of, in this case, it was growth of membership over a period of time. So it gives us the rate of change of this system. So it's very descriptive. It tells us how things are changing. And I mentioned before there were some other special lines too. So we can have both horizontal and vertical lines. And we said earlier, the slope of a horizontal line is 0 because it's like a flat line. It's a flat surface. And then we said a vertical line has no slope. But let's see how that would work out mathematically. So we have this example. We don't know anything about these two lines right now, but let's see what happens when we try to find the slope between them. So for part A, we have these 2 points, -4, 1, and 2, 1. So our x1 is -4, and our y1 is +1. Our x2 is +2, and our y2 is +1. So let's find the slope between these. Notice y2 and y1 are the same value. They exist on the same line going through the y-axis. So that's a hint that this is going to be a horizontal line. If I do y2 minus y1, that will be 1 minus 1 over x2 minus x1, 2 minus -4. 1 minus 1 is 0. 2 minus -4 is +6. 0 divided by anything is just 0, unless if we were also dividing by 0. And if we were graphing this, just a quick sketch, +1 is here, so we would have, say, like -4 over here, +1, and +2, +1, draw a line through that. It's a horizontal line. So if you see a repeated y value, that means the line is horizontal. So this gives us our property. The slope of a horizontal line is always equal to 0. And the giveaway again is the repeated y value. So let's look at part B. So now our 2 points are 2, 4, and 2, -3. Notice this time the x values are repeated. So the 2, we can call this our x1. This will be our y1. This will be our x2. This will be our y2. So let's follow the slope equation. y2 minus y1 is -3 minus 4 over x2 minus x1, 2 minus 2. Notice this time we'll get a 0 in the denominator. -3 minus 4 is -7, but 2 minus 2 is 0. So if you ever are forced to divide by 0, that will give you an undefined result. If you do this in your calculator, it will probably say domain error or something along those lines. This is undefined. So that's why we say this vertical line, if we were to graph this, I'll do a similar little sketch here. Let's say this is +2 on the x-axis. Let's call this +4 and this -3. Our points would be like this on top of each other, because they have the same x-coordinate of +2. So it's a vertical line and the slope is undefined. So we get that property. We can say the slope of a vertical line is always undefined. So horizontal lines, the slope is 0. Vertical lines, the slope is undefined. So now that we know how to find slope, let's use it to graph a line. Since I mentioned before, it's kind of like directions from one point to another. So this will be our last section. Using the slope and 1 point on a line to graph the line. Let's look at our first example. And let's remember that the slope is rise over run, or change in x over change in y. So if we have, for part A, a point of -1, -2, and the slope is 3 over 2, you can start by plotting your first point. Let me build my axes. So I can start with my first point, -1, -2. That would be down here. I'm going to use the lighter blue. And then from this point, I can use the slope to get to a second point on the line. So I know I should go up 3, so rise 3. So I can imagine going up 3 spaces and then over 2. So rise over run. So I'll go over 1 and then end up right here. So that point ends up over here, looks like at 1, +1. So again, that was up 3 over 2. And then now I have 2 points, I can just connect it with a line. So again, it's very useful. With the slope in a single point, you can graph your line very easily. And notice the slope was positive and we have an upward slanted line. All right, let's look at part B. B gives us the point 0, 1, and then the slope is -3. So let's use the same strategy. So I'll start by plotting my first point. 0, 1 would be here on the y-axis. It has an x value of 0, y value of 1. And then the slope is -3. It's just a number. So I can view this as -3 over 1. If you ever have a single number, you can just place it over 1, and that will give you that rise over run fraction. A whole number is technically still a fraction. So from this point, it means since I have -3, I would go this time down 3 and then over 1. So I should end up over here. That looks like the point 1, -2. And then I just need to connect it with a straight line. So if you're given a single point in the slope, just plot that point and use the slope in rise over run fashion to get to your next point. And you can even use it again and get a third point if you want to. And you can build your line from there. All right, that's it for this section. So we talked about what slope is conceptually, how to find slope given 2 points on the line, and again, that was our formula, y2 minus y1 over x2 minus x1. We saw some application, and that gave us this idea of slope as a rate of change over time. We discussed horizontal and vertical lines. Horizontal lines have a 0 slope, vertical lines are undefined. And then we used slope and a point to plot a line. All right, that's it for this video, and I'll see you next time.